Here I want to talk about erasure error correction. So this is exercise number 1. Let the transmitted code word be 0001111. You can check that this is a code word using the relation, and assume that first and second bits were erased. So these are XX. So you don't know what they are. They are erased. And let us decode it. So write these code word, receive the word into the circles, and let's apply the rule. And the second circle has 2 erasures, so it's not a good idea to use this first circle first. Let's take a look at this one, where you have a single eraser. So single eraser, you can completely determine what that M1 erased bit should be to have the first circle satisfied. So that is nothing but 0. This has to be. And using the same rule here, I have to M2. I have M2 set to 0, so that this equation or circle is satisfied. So both of them are 0. Then make sure that third circle is also satisfied with a 0 and 0 here. Yes, it is satisfied. So that was first erasure error correction. About erasure error correction, the other one, which is this. In this particular case, the first circle has 2 erasures, so it's not a good idea to use this first. So let's take a look at this first. And 1, 1, 1, so this has to be 1. 1, 1, 1, this has to be 1. So this is 1, 1, 1, 1. All one code word is the decoded code word. Okay, that's what I have done. Now erasure error correction, where there were 3 erasures. Can we decode this? So you write them down. So all 3 circles have 2 erasures. So you cannot determine which one to do first. So let's do just this first. So when you do this first, M1, M3 could be both of them, either both of them 0, 0, or both of them 1, 1. Those are the 2 possible solutions. And then when you have this one 0, M2 has to be 0. Okay, so M1, M2, M3, all of them zeros, or M1, M2, M3, all of them ones are 2 possible solutions. So 0, 0, 0, a solution, 1, 1, 1, a solution. So 2 possible answers. So it is not uniquely decodable. So this is not decodable. So 3 errors, 3 erasures in this particular example were not decodable. Then can we ask that in this code, all 3 erasures cannot be decoded? We have to check, right? So let's check. I have erasures on M3, P1, P2. So erasures occur this way. In this particular case, P2 is uniquely decodable because 3 things are decoded, determined. So M1, so 1, 1, 1 here, so this has to be 1. So one of P3 P2 has to be 1. And there's three numbers determined, so M3 has to be 1, 2. So two of them is completely determined. So since this has to be 1, then P1 has to be 1. So the decoded code word should be all one code word, uniquely determined. So we can say that this code can correct some 3 erasures, but not all of them. And in this particular case, all 2 erasures can be corrected, or single error can be corrected. Okay, that's the conclusion. And that's the conclusion that we can draw. And here is the summary. So challenging questions. How many bit flip errors can be corrected? This question can be answered that based on error patterns. The correct answer is that all single error patterns can be corrected, but other than that, no bit flip errors beyond a single error can be corrected. So that's the summary. And then up to how many erasures can be corrected? Up to 3 errors can be corrected, but not all 3 error patterns are corrected. But up to 2 erasures, all of them can be corrected. Single erasure patterns can all be corrected. Okay, so summarizing one more time, all 1 erasure patterns can be corrected, all 2 error patterns can be corrected. Some 3 error patterns can be corrected, but not all of 3 error patterns can be corrected. Okay, the check equations are represented in terms of circles, can be in fact written this way. So M1, M3, M4, P1 is equal to 0. M1, M2, M4 plus P2 is equal to 0, and so on. So there are 3 equations, 3 circles, okay? We use this in relation among bits to encode so that you have a code word, and then we use this relation to decode from a received word. Received word has some erasures and bit flips. Some of these patterns can be corrected. In order to increase more number of errors or erasures corrected, we need to increase more number of check bits. These equations has to be simultaneously satisfied. And this statement can be entertained. And here is a parity check matrix. Using that equations, we can obtain this parity check matrix. There are 3 equations. There are 3 rows in this matrix. This matrix is called parity check matrix. So the first equation was M1, M2, M4, P1 is equal to 0. That is represented by this first row. when you multiply first row with this code word vector, that is the first equation that we saw in previous page. The second equation, which is M1, M3, M4, P2, sum up to 0, is represented as this second row in the parity check matrix. And the third equation is represented by this third row. So when you have a code word following this relation, when we multiply code word with a parity check matrix, it should be equal to 0. So you have parity check matrix H. When you multiply code word with a parity check matrix, it should be equal to 0. So when you have received the word which has some error pattern added to it, so HR is equal to H parentheses C plus E parentheses closed, that is HC plus HE. HC is equal to 0, so what's left is HE. And we call this HE, so it is 3 by 1 vector S, and we call this vector S syndrome. When syndrome is not equal to 0, that means there is some error in the received word. And for a single error pattern, so out of these 7 places, only one position there is 1, other than that position, all else are zeros. That syndrome is unique. So for example, when M1 is equal to 1, rest of them 0, syndrome is the first column vector, 1, 1, 0. When syndrome is 1, 1, 0, the first bit has to be flipped because there was an error. When syndrome is 1, 0, 1, that means second bit was an error. When syndrome was 0, 1, 1, third bit was an error. When 1, 1, 1, fourth bit, 1, 0, 1, fifth, sixth, and seventh. So you can correct all single bit error pattern. Okay, that parity check matrix can also be represented as a bipartite graph like this. So this one says M1, M3, M4, P1, they all add up to 0. So that's the first check equation. And the second check equation, M1, M2, M4, P2 is equal to 0. Third check equation, M2, M3, M4, P3 sum up to 0. So this parity check matrix is bipartite graph. They are all equivalent for this check equation. So these are all equivalent representation. And there is called standard array. In this standard array, where you have a message bits starting from 0, 0, 0 to 0, 1, 1, 1, 1. So there are 2 to the power of 4 code words right here. So when you have a message, then you have a P, the parity check part, uniquely determined. So these together, these 2 together form a code word. There are 2 to the power of 4, which is 16 code words. And then along this axis, we have no error pattern. So 0, 0, 0, 0, 0, 0. 7 zeros, so no error. And then you have a single error pattern, 7 of them. So you have 8 of these, and 2 to the power of 4 of these, 2 to the power of 3 of them. So these entries, there are 2 to the power of 7 words. So for each code word, you add these error patterns. So no error, single error patterns. You have a unique received word. You have another code word, you add these error patterns. So for example, 0, 0, 0, 1, 1, 1, 1, you add this, then you have exactly the same as this. And then this one says, flip the last bit. So you flipped it. Flip the second last bit, you flipped it. Flip the third last bit, you have done that, and so on. So these are the one bit distance neighborhood of this code word. These are the 1 bit neighborhood of all 0 code word. And so on and so on. You can do that throughout the whole 16 rows. You have a complete standard array. And here, each word appears once and only once, never occurs twice. So it makes up 2 to the power of 4 times 2 to the power of 3, which is 2 to the power of 7 words that are possible. So as you have seen from here, you can correct all single error patterns, flip it error patterns, because of this mechanism that we see here. Okay. Now there are some end of note problems for Heung-No code. These 4 questions have been answered, but you can ask yourself and remember and see if you can prove or disprove. And here is a little bit challenging, but using the materials discussed so far, you should be able to find out the answer to this problem. So the most difficult one is this one. Find the probability of information bit error using 7-4 Heung-No code. So assume the message bits are equiprobable. So that's the end of the note for Heung-No code.